So what I was going to talk about today is momentum equation. So where we left things last time, we talked about Reynolds transport theorem, how that reconciles the Lagrangian and Eulerian descriptions of the fluid flow. So basically whether we follow collection of fluid particles, physical particles, or the control volume that's fixed in space. And Reynolds transport theorem allows us to consider both of them coinciding at a particular instant in time, and this is where the equations are coming from. So we looked at the conservation of mass, which is the kind of easiest equation to start with. It's very elegant also, and conceptually easy to grasp. The equation that we will be dealing mostly in the course is conservation of momentum, and I'm going to start from an example because it's easier to follow, I think, the logic of derivation if we start with the particular case. That's kind of we can keep in mind, and then we can generalize it to kind of an all-encompassing case. So let's consider momentum equation for a parallel 2D flow. So the momentum equation, as I mentioned last time, is just Newton's second law. So it's mass times acceleration equals the sum of the forces acting on that control volume in space. And mass we consider per unit volume, which is density. So we write it in the form density times acceleration equals sum of the forces. And conventionally we just divide by density throughout. So we write the conservation of momentum as acceleration equals 1 over rho times sum of the forces. And we know what to do with acceleration. It's local acceleration plus convective acceleration, as we discussed earlier. But sum of the forces is a little bit tricky. And also, jumping ahead, we need to relate those forces to velocity. So that's pretty much the name of the game in derivation of the momentum equations. So let's consider a control volume in 2D, which is, and let's just make it a square, and let's say it's a differential volume with the dimensions dx and dy in x and y respectively. And let's consider the forces that act on this control volume and only consider the x direction forces, just for simplicity. So let's take care of the body forces. So we'll assume that there is a force acting in some general direction, and we'll call that g, because gravity is an example of a body force. We can decompose it into an x and y component. So this would be gx and this is gy. So gx is what we're interested in. So that's fairly straightforward. The other forces would be normal and tangent forces. And let's consider this left face of the control volume first. And on that face acts a normal force in x direction. It's pressure, and it acts on the entire area of that face. In 2D, it's just the length, dy. So there is if this is P acting on this face, so what is the force that acts on this location, which is dx away? That force is P plus dp dx, and it acts on the entire area dy again. So where does that come from? This expression, just notice that this is consistent with a Taylor series expansion of function p. Let's say you have a one-dimensional function f, just very general, as a function of x, and it's something like this, and you have some point x0 and the value of the function at that point is f0. So let's say you know that, and the function is sufficiently smooth in the neighborhood of x0, meaning that close enough to x0, derivatives of that function exist. And it means sufficiently smooth. In fact, the condition for Taylor series expansion is infinitely smooth. So derivatives of any order exist. So there are no jumps in any of the derivatives. Then we can actually find the value, express the value of the function at the neighboring point x0 plus dx as a series. The nth term is going to be 1 over n factorial nth derivative of f with respect to x at point x0 dx to the n, and etc. So it goes to infinity, and you can express the rest of the terms in various forms, Lagrange, Cauchy, and things like that. But one thing to notice, and this is actually an important concept in CFD, because this is how we replace derivatives with differences. Ultimately, we truncate the Taylor series. You notice that the magnitude, absolute value of the terms in Taylor series decreases with the order of the term. Well, one is there is a factorial of n in the denominator, which becomes larger and larger, and that brings the magnitude down. Also, dx to the power of n, right? Dx, we said it's in a small neighborhood. This whole thing is valid in a small neighborhood of x0. Dx is small, so we can assume less than unity. So you raise this in a higher power, that factor becomes very small. So the contribution of any subsequent term to this estimate of f of x plus dx becomes less and less. So at some point in CFD, for example, we just truncate the series and say that this is a good enough approximation. This is how we and solve for the derivative that we're interested in. So that's ultimately how we replace partial differential equations with algebraic equations. We replace derivatives with differences. But you could see that what we're talking about here analytically is consistent. So this our control volume in the schematic above is small. In the x direction, we're going from the left face of the square to the right face of the square. The distance is dx. So that's differential change in pressure. So these are the normal forces that act on in the x direction. There is also a shear force. So on the bottom face of the volume, on this face right here, there is a shear stress, tau, and it acts on the entire surface or area of the face. In 2D, it's the length of the segment, which is dx, and it's balanced on the top by tau plus d tau dy times dy times dx. Acceleration, we talked about this, has two parts: local acceleration du dt plus convective acceleration, which is u du dx plus v du dy. It's equal minus 1 over rho dp dx. This is what remains when we balance the pressure terms, plus the gravity, the body force, plus the tau, right? What remains of tau. And let me write down the expression and I'll explain where it comes from. I mentioned at the beginning that we need to relate that the forces to the velocity. And for Newtonian fluids, shear stress is proportionate to the strain rate. And this is not true for all fluids. So for some fluids, the shear stresses are not proportionate to the strain rates. This proportionality coefficient may not be a constant. For example, viscoelastic or viscoplastic fluids behave differently. But we're not going to go into details of those non-Newtonian fluids in the course, but it's a fascinating subject. Some of the viscoelastic fluids can be classified into shear thinning or shear thickening. It's basically the more stress you apply to a fluid, the less viscous it becomes. This is the viscosity decreases, that's a shear thinning fluid. If the viscosity increases, it's shear thickening fluid. An example of a shear thinning fluid that I'm sure you're all familiar with is ketchup. Ketchup is distinguished from a tomato sauce by the fact that it's a non-Newtonian fluid, so I think it's very commendable. Intuitively, you apply a force to a ketchup and it becomes less viscous, and this is why if you have ketchup in a glass bottle and you invert it, intuitively we deal with Newtonian fluids like oil, water, etc. And we expect a certain flow rate when we invert a ketchup bottle, and it doesn't happen because it's too viscous. And then you start shaking it, you apply acceleration, and too much of it flows down into your plate. And this is because the viscosity decreased disproportionately. So that's how it happens. An opposite example, shear thickening fluid, is a cornstarch. You apply acceleration to it, for example, you hit it and it becomes almost solid, much more viscous. Anyway, there was a great episode of Mythbusters a few years ago when they could just run across a pool of cornstarch or something like this, because when they pound the surface of that liquid with their feet, it becomes too viscous for the body to sink for a moment. So things like that. Fascinating applications. Many biological fluids, like blood, for example, at small scales is non-Newtonian, because when our capillaries, the blood vessels, the diameter of those is on the order of the diameter of red blood cells. The red blood cells behave like water-filled balloons. They can be squeezed down through the small capillaries, and essentially that deformation decreases viscosity effectively of the fluid. So it's a shear thinning fluid. Many other biological sticky things like saliva, the things that you could kind of put saliva between your fingertips, separate them, and you will see strands. And this is the non-Newtonian fluid behavior. Anyway, all this long story short, that we're not going to talk about this in this course. So we're going to constrain ourselves to Newtonian fluids. And so this is how the derivation generally goes. In general, if you look at the Navier-Stokes equations, and I'm going to, at the moment, forego the derivation of the complete Navier-Stokes equations, but take a look at how it looks like in general. Well, notice, of course, that there are three equations for x, y, and z direction. So you combine this typically with a continuity equation, which is for incompressible flow is just this. So we have four unknowns, which is u, v, w, and pressure, and four equations. So three Navier-Stokes momentum equations and one continuity equation. That allows us to solve the fluid problem.